of FARHANSYAMIL.
My name is MOHAMMAD IMRAN AZMAN.
My name is MOHAMMAD FADZIL.
So today our group will present to you about one of the steady flow devices, which is turbine.
In our class, we study that turbine is one of the steady flow engineering device. Steady flow process is defined as process during which a fluid flows through a control volume steadily. So there is no output energy. Then in steam, gas or hydroelectric power plants, the device that drives the electric generator is the turbine. As the fluid passes through the turbine, work is done against the blade which are attached to the shaft. As the result, the shaft is rotated, then work done is produced.
Okay, now I will tell about the formula related to the turbine. So, the rate of energy in equal to the rate of energy out, and the work of input plus with the rate of mass times with the enthalpy 1 equal to the rate of heat out plus with the rate of mass times with the enthalpy 2. And we assume that kinetic energy and potential energy is equal to 0. So, turbine used to produce rotating shaft power. So, this is the basic design of the turbine. For example, the fluid enters at the inlet and exits at the outlet, and the turbine will produce rate of work. And the typical execution for the turbine is the rate of mass at the 1 equal to the rate of mass at the output. And the second, potential energy is equal to 0. And third, rate of work is more than 0. Except as an exception, rate of heat equal to 0. And the energy equation is rate of work equal to the rate of mass times with the first enthalpy minus with the enthalpy 2 plus with the half of the volume 1 squared minus with the volume 2 squared.
Okay, so for the question 1, the question is the power output of an adiabatic system turbine is 5 megawatt, and the inlet and the exit condition of the steam are as indicated in figure above. ISMAIL. So for the question 1, they ask us to compare the method of enthalpy, kinetic energy, and potential energy. For question B, determine the work done per unit mass of the steam flowing through the turbine. And for the question C is calculate the mass flow rate of the steam. Okay, so from the figure, we get information that the P1, which is 2 megapascal, and temperature 1 is 400 degrees Celsius. From the properties table, at table A6, we get the enthalpy 1, which is 3248.4 kilojoule per kilogram. So at the turbine exit, we obviously have a saturated liquid vapor mixture at 15 kilopascal pressure. So we want to know the enthalpy of at the outlet, which is H2. So we can calculate using this formula, and we will get 2361.01 kilojoule per kilogram. So we want to calculate the change of enthalpy. So we minus the enthalpy H2 minus enthalpy 1. So we will get negative 887.39 kilojoule per kg. So for change in kinetic energy, we use this formula. So we substitute the value in this formula, and we will get 114.95 kilojoule per kg. For change in potential energy, use this formula and we substitute the value and we will get negative 0.04 kilojoule per kilogram. Yes. So for the question B, we need to determine the work done per unit mass of the steam flowing through the turbine. So from the equation for the work done is change in negative change in enthalpy plus with change in kinetic energy plus with change in potential energy. So change in enthalpy we can these three we can get from the answer from A, which is change in enthalpy, change in kinetic energy, and change in potential energy. So the value we substitute in here, so we can get the work done, which is 872.48 kilojoule per kilogram.
Okay, for this equation, we need to find the mass flow rate of steam. So we use this equation, and for the equation formula for the rate of work out, we use this 5 megawatt power. We change it to the 5,000 kilojoule per second, and for the work done out, we use previous answer, 872.48 kilojoule per kilogram. So we substitute and we find the answer is 5.73 kilogram per second.
Okay, for the question 2, steam expands in a two-stage adiabatic turbine from a specific state to another state. Some steam is extracted to the end of the first stage. The power output of the turbine is to be determined. Okay, for the assumption 1, this is a steady flow process since there is no change with the time. For the assumption 2, kinetic and potential energy change are negligible. For the assumption 3, the turbine is adiabatic and the heat transfer is negligible.
Okay. From this diagram, we can extract this given information, which is we can list down for each condition, and then using this given information, we can get H1, H2, H3 by referring to the table of properties A5 and A6. Okay, the question is about the power output of the turbine is to be determined. We take a look at its analysis. We take the entire turbine, including the connection part between the two stages as the system, which is a control volume since mass crosses the boundary. Nothing that one fluid stream enters the turbine and two fluid streams leave. The energy balance for this steady flow system can be expressed in the rate form as this equation. And we know that this equation will be equal to 0. Hence, we get energy balance equations. By using these equations, we expand it as this, and then in the equation we have to look for the power output, which is this one. So we make it as its title. Next, substituting the power output of the turbine is, we can get this, and then by substituting its H, which 2 is 3, we get its answer 17.8 megawatt.